From the soaring heights of the Burj Khalifa to the sprawling motorways of Riyadh, we have built our modern world on a paradox. We use the most durable material known to man, concrete, to build structures we know will eventually fail. Welcome to Curious Minds podcast, and I'm Omar. And in my career in construction, I've learned one hard truth: concrete always cracks. It's not a matter of if, but when. We've built our entire modern civilization, our homes, our stadiums, our massive flyovers, on a material that is essentially destined to fail the moment it dries. Concrete is the second most consumed substance on Earth after water, but it has a fatal flaw. It's brittle, it cracks, and those cracks are expensive. This isn't just a local headache, it is a global epidemic of crumbling infrastructure. To give you a sense of the scale, let us look at some of the facts. United Kingdom is facing a maintenance backlog that has reached a record £16.81 billion, with the RAC attending over 25,700 pothole-related breakdowns in the last recorded 12-month cycle. Latest reports from India show that potholes claimed 2,161 lives in 2023, a tragic 16.4% increase from the year before. United States 2025 report card gives our roads a D+ grade, noting that 39% of major roads are in poor or mediocre condition. In South Africa, independent estimates from the AA suggest there are well over 25 million potholes, a 67% increase over the last 5 years. And authorities like SANRAL highlight that fixing reported holes remains a top priority. But what if our cities were more like our bodies? When you cut your skin, you don't stay open forever. You bleed, you scab, and you heal. Imagine a bridge that does the same. Today, we're looking at the one transformative idea. Infrastructure is no longer just about dead weight. It's about biological resilience. We're moving from a world of chips and screens to a world of mud and bacteria. To understand how we fix this global maintenance crisis, we have to go to a lab at TU Delft in the Netherlands. Meet Professor Henk Jonkers. He's a microbiologist who looked at a limestone cave and thought, why can't a building do that? The secret ingredient isn't a new chemical, it's a tenant, specifically specialized bacteria from the Bacillus genus. Imagine we are mixing a fresh batch of concrete for a new skyscraper in Mumbai or a bridge in London. Along with the sand and cement, we drop in tiny capsules. Inside, these specific bacteria, tucked away in a deep dormant sleep, research shows they can stay under the covers, completely inactive for up to 200 years. They're waiting for the alarm clock to go off. Let's look at the how through a 4-step play. Step 1. A heavy truck rolls over a bridge. A tiny hairline crack forms. To the naked eye, it's nothing. To the bridge, it's the beginning of the end. Step 2. Rainwater seeps into that crack. It hits the capsules and dissolves them. The water wakes up our sleeping bacteria. Step 3. The bacteria wake up hungry. They consume a specialized nutrient mix, calcium lactate, provided right in the concrete. And here is the magic. As they digest that food, they produce calcium carbonate, better known as limestone. Step 4. This limestone grows and hardens, physically filling the crack from the inside out. In a laboratory, this can happen in just 7 days. Outside, it typically takes several weeks. The concrete has literally grown new stone to heal itself. Think about the shift in perspective here. Usually when we think of smart cities, we think of 5G towers and digital sensors. But this is a different kind of smart. It's a biological if-then statement. It turns a static, dying material into a living, responsive ecosystem. I know what you're thinking. I've heard the questions in the boardroom. Let's address them head-on. How many times can they heal? The answer is as long as there is food. If a crack heals and then, years later, a new crack forms nearby, the bacteria can reactivate. As long as the nutrients remain in the matrix, the process can repeat. What if the limestone itself breaks? Limestone is brittle. If the scar tissue cracks again, the dormant spores nearby simply wake up and start the process over. It's a continuous biological surveillance system. What about the waiting period and damage limits? Bioconcrete is a specialist. It's designed to seal cracks up to 0.8 millimeters wide. It's not for a bridge collapse, it's medicine for the silent killers. Those micro cracks that let salt reach the steel rebar and cause internal rot. Are there environmental limits? Great question. These bacteria are hardy, but they are living things. In extreme Arctic cold or bone-dry deserts, their healing speed can slow down significantly. Engineers are currently working on cold climate strains to ensure the bridge in Oslo heals as fast as the one in Dubai. What about demolition? At the end of a building's life, bioconcrete is crushed just like traditional concrete. Research from the NICER program led by UCL suggests that mineral-based construction materials can be effectively managed within a circular economy, emphasizing the potential for safe aggregate reuse as these technologies scale. Let's talk about the real cost. Standard concrete is cheap. Bioconcrete currently carries a significant material cost premium. However, we must look at the life cycle value. If we can reduce maintenance by up to 50% or extend a structure's life by decades, the math starts to look very different. The global market is already reflecting this, with projections reaching over $100 billion by 2026 as the industry pivots to durability. What connects a lab in the Netherlands to a construction site in São Paulo or a highway in Sydney? It's the realization that we've been fighting nature for too long, the aha moment. We don't need to build things that are indestructible. We need to build things that are restorable. By partnering with biology, we're creating a world where our infrastructure mimics the very life it's meant to protect. Looking ahead, picture this. In a decade, the pothole crew might be a thing of the past. We might walk on roads that heal after a winter freeze. Speculation? Perhaps, but grounded in the early success of self-healing structures already standing today. It calls for a new kind of collaboration, architects working with microbiologists, civil engineers talking to biologists. We are building the forever city, one limestone producing bacteria at a time. So here is your reflection for the week. Next time you walk over a bridge or down a city street, don't just see the grey slabs. Think about the potential life hidden inside. If a block of cement can learn to heal itself, what does that say about our own ability to adapt and repair the cracks in our world? I'm Omar. This is Curious Minds Podcast. Thanks for listening. Stay curious, stay resilient, and stay kind. See you next week.